Alright, hello class. In this video we're going to be talking about approximating area under curves. So this is going to round out and start the process of finishing the integration module for this particular course. So you might wonder why we're suddenly talking about approximating, and there should be two P's there. All right, there we go. Why we would be talking about approximating area when we've been discussing antiderivatives and integrals, which is sort of the reverse of the derivative. And the reason is essentially what area can actually represent for us. So let's do a very simple physics example, and you'll see why we might want to start talking about area under curves. All right, so let's suppose that a car travels at 70 miles per hour for 2 hours. So we're assuming a constant rate of change here over a 2-hour span. Now, if we want to find the displacement of the car, right, after 2 hours, well, displacement, if you're always sort of have a positive orientation, displacement's pretty much the same as total distance traveled, but the displacement of the car is basically going to be, we'll take our 70 miles per hour, right, and we'll multiply by the 2 hours so that the hours cancel and we'll be left with 140 miles. Okay, so we're basically multiplying to get the displacement, and in this case it's the total distance traveled. So if we instead looked at a graph of this, well, if on the horizontal axis we let this be time, so that's going to be in hours. And if we let the vertical axis be the velocity, right, and we were to graph this 70 miles per hour, well, it would just be a constant, right, for, say, 1-2 hours. And let's pretend there we go. Okay, so let me do this. So here we have 70 miles per hour as our function, right? We have a constant rate of change here, and it's over the 2 hours. Now, if we found the area between this curve and the t-axis, okay, that area is going to correspond with the displacement, right? The area will be the base times the height. So the base in this case is, say, 2 hours, while the height is 70 miles per hour. So the area actually comes out to be 140 miles, which is the displacement. All right, which is kind of an interesting result, that it's actually the area that the graph of the velocity makes corresponds with the displacement of the, say, object in question. Okay, so in general, if v of t is the velocity of an object, then the area between the graph of v of t and the t-axis gives us the displacement of the object over the given time period. All right, so say we have the graph of the velocity of an object, and we look at the area beneath the graph, or between the graph and the t-axis, which we typically call beneath or under. And let's say we're looking at it from t equals a to t equals b. This area corresponds to the displacement. right? So this is the displacement over the interval a to b. In other words, if s is the position function, it's going to be s of b minus s of a. So what this area does is the area kind of joins the velocity, because it's the area beneath the velocity, and it gives us information about the position. Okay? So in other words, we are getting, through the area beneath the curve, we're getting, or at least going from the velocity to the position through this area. Now, when we've been doing this before is with integration. So it seems reasonable to assume that there's some sort of integral happening here, right? So there's probably integration of some kind happening in this step. Okay, so this is exactly why we want to start talking about the area beneath curves, because the area beneath curves will correspond with the integral. It's going to be directly related to integration. Now, how that is, we will talk about in the next lesson or two. But for right now, what we want to really talk about is how do we find these areas, right? If this is going on, how do we find areas beneath crazier situations? And it doesn't just have to be velocity and displacement. It can be really just any derivative in the original function. All right, so in other words, if we have the graph of f prime, right, and we take a look at the area beneath the graph of f prime from, say, a to b, okay, and take a look at the area of this region, okay, is going to be the same thing as f of b minus f of a, the change in f over this interval. Okay, so it doesn't just have to be velocity. It could be anything that we're talking about, as long as we are talking about the change. And then that area beneath that curve is going to represent, well, you can almost think of this as the overall absolute sort of change in the f of b minus f of a. That would technically be delta f over the interval a to b. All right, so once again, the question becomes, well, how do we get the area of these weirder things? And for right now, the best we can do is actually approximate. All right, and if we need to approximate the area beneath the curves, how do we go about doing that? Well, it may seem kind of like a hacky or janky way to do it, but actually we just use rectangles, okay, to help us. Okay, so what do I mean? Well, what we end up doing is, if I wanted to approximate the area beneath this curve, well, we could do so with some rectangles, right? We could, let's say this rectangle, then maybe use this rectangle, then this rectangle. Okay, and then maybe here use this rectangle. So we would just maybe throw a bunch of rectangles beneath this curve, and the area of these rectangles summed together, okay, the sum of these will be approximately the area or equal to, or the area under f of x. Now, you'll notice that the way I drew these rectangles here give me overestimates for a little while, but then these give me some underestimates, right? So it's not going to be perfect, okay, but it should eventually balance out. Now, here's the thing we usually do, though. Okay, notice that these rectangles I drew were kind of mismatched, right? What we usually do is we usually set these up to be set them up to have equal bases, right? So we will typically split the interval into an equal number of bases, and then we will make the rectangles with bases of all the same sides. Now, the question then becomes well, where do we get the height of our rectangles from? Okay, and I didn't draw this perfectly, but so where do we get the height for our rectangles? Well, there are a few ways we could go about doing it. One, this is what is called a right-handed estimate, as we use the right-hand side. So here, I would use the right-hand side here, 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 like this. Okay, so that would be a right-handed estimate where we use the right-handed pieces. So if this is A and this is B, okay, what we will typically do is then maybe have an x1, x2, x3, x4, x5, x6, x7, x8. This would be x9 and A would be x0. We would start our heights with f of x1 all the way up to f of x9. Okay, but if we were going to use the left-handed estimates, well, here we would use the left side of the propositioned intervals. And notice that the difference here in this one is actually almost negligible. Okay, and so here we would start at this endpoint as our height, and we go all the way up to f of x8, and those would be our heights. Okay, but another way we can actually do this is taking the midpoint and using that for the height. Okay. Now don't worry, I am actually going to do an example showing how this works. Okay, but I just want to kind of get the overall idea out of the way. And for that, we would use the midpoint of these subintervals that we've created. So we also have a midpoint estimate. Okay, now notice that these will all be very close, and you'll notice that these, well, the midpoints kind of do overestimates and underestimates at the same time. The right and left will swap when they're doing over and underestimates. But here's the main idea. Okay, the main idea is that if we use even more rectangles, say we use much smaller but a larger number of rectangles, right? So say we're doing some right-handed estimates here, but with much smaller rectangles. What we hopefully see is that the smaller the bases of the rectangles get, the more rectangles we will have, and the better the approximation is going to be, because our overestimates, we have maybe more of them, but they are all much smaller. So the idea, okay, is the more rectangles you use, the better our approximations will be, and the better the right-handed estimate, the left-handed estimate, and the midpoint estimates will be to one another. They'll get closer and closer as we use more and more rectangles. Okay, all this stuff is actually called a Riemann sum, or Riemann estimations. Okay, there's right-handed Riemann sum, left-handed Riemann sum, midpoint Riemann sum. There's also many other ways we can approach this, and I I should just show you an example of how this works, how we do this approximation, and hopefully that will kind of clear things up a little bit. All right, so let's suppose that the velocity of an object is given by v of t equals t squared, where t is between 0 and 8. And we want to approximate the displacement by dividing the interval 0 to 8 into n equal subintervals. So we're going to look at it in 3 different cases, where n is equal to 2, n is equal to 4, and n is equal to 8. So we want 2 subintervals in the first part, and 4 in the second, and 8 in the third. So to do that, we're looking at the interval 0 to 8. Okay, if we want to split it into 2 equal subintervals, that means we're cutting it in half. So we're looking at 0 to 4 and 4 to 8. Okay, now, so that's for the first part. For the second part, if we're going to split it into 4, okay, that means we are looking at the interval from 0 to 2, from 2 to 4, from 4 to 6, and 6 to 8. All right, so the intervals in pink are what we'll be looking at for the second part. And for the third part, if n is equal to 8, well, that's going to be 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and 7 to 8. So that's what we'll be looking at in the third case. Now, there's a nice little formula that helps you. So if you want to split, okay, if you want to split any interval a to b into n equal subintervals of length delta x, so that's what we call the step size of each one of these bases for the rectangle, then delta x is equal to b minus a all over n. Okay, so for n equals 2, and our interval is 0 to 8, okay, delta x is going to equal 8 minus 0 all over 2, which will end up being 4. So the length of each subinterval in our first case for part A is 4. Okay, so that means we'll be looking at 0 to 4 and 4 to 8. Right, so our delta x in this case is 4. Okay, so to show this on a graph, here is the graph of, it's labeled F here. We don't need to really show that. But here's our t squared. Right, if we split this into 2 subintervals, 0 to 4 and 4 to 8, we have 3 ways that we can draw our rectangles. Okay, we can draw them this way, where the height is chosen on the right side. Okay, so maybe it's helpful if I split it up first. So we're looking at it from 0 to 4 and then 4 to 8. So when we make our rectangles, we can either use the right-hand side to get our height, the left-hand side, or the midpoint. So to start with, here is the right-hand side. So we split the interval in half, and then we get our height from the the right-hand side. So this first height here is going to be f of 8, and the other half is going to be f of 4. Okay, so to give you an idea here, we made a rectangle using this height here. So this would be a height of f of 8, and then we used this height here, which was an f of 4. So we've made 2 rectangles, okay, of base 4 and height f of 8 and f of 4. And I'm calling it f. This is actually v, so I should probably be a little more conscientious there. So the area of the first one and the second one, well, A1 is going to be the base 4 times V of 4. The area of the second one is going to be the base 4 times the height V of 8. Okay, and so this will be 4 times 4 squared, and this will be 4 times 8 squared. All right, now the sum of these areas, and this is a right-handed estimate, right, is going to be 64 plus 256, which is 320. Okay, so now let's look at a left-handed estimate. All right, back to our graph. If we look at the left-handed estimate, we'll get this. We're using the height of the left side of our interval. And notice on the left side here, it's going to be V of 0 and V of 4. Well, V of 0 is going to be 0, so we only get this rectangle. Okay, so for the left-handed estimate, we get this V of 0 as one of our heights, and then we get V of 4 as our other height. So notice V of 4 is being used twice here, but V of 8 is not. Okay, so for our left-handed estimate, it's going to be the base 4 times V of 0 plus the base 4 times V of 4. Okay, so it's going to be V times 0 squared plus 4 times 4 squared. So this goes to 0, and that's just 64. Okay, so there's our left-handed estimate. And the next thing we could do is use the midpoints. So, oops, wrong one. With the midpoints, we have the same subinterval, but we're taking the halfway point as our height. So we'll use V of 2 and V of 6 to find our heights. Okay, so we're going to be somewhere in the middle doing it this way. Okay, so the midpoint estimate, right, and we're getting our height from the midpoint. So halfway between 0 and 4 is V of 2, and halfway between 4 and 8 is V of 6. So it'll be the base times V of 2 plus the base times V of 6. So it'll be 4 times 2 squared plus 4 times 6 squared. So this is going to come out to be about 160. Okay, so we got very different estimates here, right? But that should hopefully make sense because we're only using 2 rectangles to do this. We're way off. But if we just look at the right-handed estimates here, and instead of only using 2 subintervals or rectangles, we double it to 4, we'll already see that we have a much better estimate this way. All right, so this is what brings us to part B, where we want 4 subintervals. Right, so our intervals are 0 to 2, 2 to 4, 4 to 6, and 6 to 8. And notice this is the right hand in red, and we are getting our heights from the right-hand side of the interval. Okay. Similarly, if we look at the left-handed and double the number of rectangles to 4, once again, we see a much better, much closer approximation showing up. And then also, if we look at the midpoint and double the number of rectangles, once again, we get a much better representation. And we'll get an even better one when we look at 8 subintervals. Okay, so when n is 4 subintervals, our delta x, which is the length of our subintervals, will be the b minus a all over n, or in this case 8 minus 0 all over 4 in this case. So we have 8/4, which is 2. So that's the length of the intervals. Okay, so what I want to show is a quick way you can do this without having the graph. I have the graph in the other window, so this is 0, this is 8, right? And we're looking at 0, 2, 4, 6, and 8. So when we do the right-handed estimates, okay, well, the base on all of these is 2, right? That is going to be the true for all of these. And when we use the right-handed side, we use v of 8, v of 6, v of 4, and v of 2. We don't use v of 0 for a height. All right, so if we go back to the graph and look at the right-handed estimates, right, v of 8, v of 6, v of 4, v of 2. Okay, so the area of all these rectangles, well, it's so delta x, which in this case is 2 times v of 2 plus 2 times v of 4 plus 2 times v of 6 plus 2 times v of 8. So notice we could actually factor out the 2 and just have 2 all times v of 2 plus v of 4 plus v of 6 plus v of 8. Okay, and so this is basically 2 plus, this will be 2 squared plus 4 squared plus 6 squared plus 8 squared. All right, which gave us 240 when we sum that up. It turns out we can do this for all of these. We can actually factor out that base, and we set it up specifically so we can do that. It's because we use that same delta x for all of these. Okay, now next, if we want to do the left-handed estimate, well, now if we just go back to what we were looking at, instead for the left-handed estimate we start here. So we'll look at v of 0, v of 2, v of 4, and v of 6 to get our heights. We won't use the rightmost because we're doing a left-handed estimate. So the left-handed estimate, it will be 2 times v of 0 plus v of 2 plus v of 4 plus v of 6, which will be 2 times 0 squared plus 2 squared plus 4 squared plus 6 squared, and that's going to be about 112. Okay, so right now we're looking at the difference between 112 and 240. That's much closer than what we got last time. All right, and finally, for our midpoints, well, we clear this out. And, well, midpoints, it's what it sounds like. We use the halfway point of these intervals. So we'll use v of 1, v of 3, v of 5, and v of 7. Okay, so the midpoint estimate is going to be 2 times v of 1 plus v of 3 plus v of 5 plus v of 7. All right, so we'll have 2 plus 1 squared plus 3 squared plus 5 squared plus 7 squared, which comes out to be 168. So just to look at it on the graph here, there we go. That's what we'll get. And you can see it. We get the height from 1, 3, 5, and 7. All right, next up, we'll look at part C, which is for 8 subintervals. We go back to our graph for the right-handed estimate. Instead of the 4 subintervals, now we're going to be looking at 8 subintervals. And you can see the difference between those okay, we start getting much closer estimates, or we should, when we get more rectangles. So here at 4, you see how much we are an overestimate of the area is much larger than when, say, we go to 8. All right, so for 8 subintervals, remember our delta x is going to be b minus a over n, so it's going to be 8 minus 0 over 8, so 1, right? So we'll go from 0 to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so when we do the right-handed sum, okay, so the right-handed sum, remember we start on the right side, so we'll use v of 8, v of 7, v of 6, v of 5, and all the way up to v of 1, but we won't include 0. Okay, so for the right-handed estimate, right, it's going to be our delta x, which in this case is 1. So it'll be 1 times v of 1 plus v of 2 plus v of 3 plus all the way up to v of 8. All right, so it's going to simply be, we can drop the 1 times all that. It's just going to be 1 squared plus 2 squared plus 3 squared plus all the way up to 8 squared. And so, all right, so I got about 204 when I plug that into my calculator. Okay, so there's the right-handed estimate. Let's look at the left-handed estimate. All right, left-handed estimate, again, we'll start at 0. We'll use v of 0, and we'll go all the way up to v of 7, but we won't use 8. Right, so we'll use 0, 1, 2, 3, 4, 5, and 6. Okay, so our left-handed estimate will be the 1 times v of 0 plus v of 1 plus v of 2 all the way up to v of 7. Okay, which will be 0 squared plus 1 squared plus 2 squared all the way up to 7 squared. Now, you might think that, hey, this is going to be the same thing we got before, but without the 8 squared, so we could just subtract away the 8 squared and then plug in the thing we're missing. Yes, you can do that. Okay, there are lots of little tricks you can use to help yourself here, or you can just crank it out the long way every time. It's not that big of a deal, right? As long as you get to the right answer here. All right, so I got about 140. All right, so there's our left-handed estimate. And now let's set up a midpoint estimate. Of course, before we do that, let's take a look at the graph. Here's our left-handed estimate at 4, and then when we move to 8, we see, okay, we're getting much closer, right? Now, we're going to look at the midpoint. So here's our midpoint with 4 subintervals. But when we move it up to 8, we see, well, we're getting closer and closer approximations. In fact, when you look at all these side by side, right, the more rectangles you get, the closer they end up being. Okay, so for our midpoint estimate, well, again, we take the midpoint of every region for our height, right? So we'll use v of 0.5, v of 1.5, v of 2.5, etc., all the way up to v of 7.5. Okay, so our midpoint estimation is going to be, again, it's the same delta x down here, right? It's still the 1, but it'll be v of 0.5 plus v of 1.5 plus v of 2.5 all the way up to V of 7.5. So this one is definitely nastier looking, right? Because it's going to be 0.5 squared plus 1.5 squared plus 2.5 squared plus all the way up to 7.5 squared. Right, so I ended up getting about 170. All right, let's kind of compile these results together and see how they stack up. All right, so here I've made a little table of basically n, our number of subintervals, what our right-handed estimate is, left-handed estimate, and the midpoint estimate. And I went a little further than what we've already done. Okay, I went to 16 and 32, spared you the details there. But as you can see, at 2 subintervals, the right-handed estimate starts really high at 320, but then starts decreasing down to about 178, it looks like. While the left-handed estimate starts much lower at 64, but starts increasing up to 162.75 at 32 subintervals. And then the midpoint estimate starts at 160 between them and stays pretty much between them, but is also moving towards about 170.625. This is something you can see on the graph as well. Right, if we look at the graph here, I have all 3 rectangles kind of going at once, or all 3 estimates going at once, and you can see their numbers. But as we increase our n, you can see that the rectangles themselves are getting closer and closer and closer together. Okay, so here we are at n equals 32. All right, and we see how much closer all of these rectangles have become. Right, and if we take it even further, say up to, let's go all the way to 64. Right, when we go all the way to 64, we see we get to something even closer. Right, these rectangles, we're getting more and more rectangles. So here we have 64 rectangles, and the differences between, see, these upper estimates and these lower estimates are getting smaller and smaller and smaller. Okay, and if we take it out even further, right, eventually, right here, we are at, this is 512 rectangles. And you can see that the difference is very small. We've gotten it down to the difference in about 1. Right, we have 170.1, 171.2-ish, and 170.7-ish. Okay, so, but from a sort of far away angle, we can see that the difference between these upper estimates and lower estimates get so small. Okay, we have to zoom way in to see the difference here. And so this is essentially what this Riemann estimation is all about. These Riemann sums are all about. The idea is that the more rectangles we have, the better approximation we'll get, and the closer together the right hand, left hand, and midpoint estimates get. Right? They start to get closer and closer and closer together. Okay, so if we go back out to, say, 2, actually, no, I'm sorry, this is n is equal to 64 versus n is equal to 512 when we're zoomed in. Okay. But the main idea here is that if you like sort of squint at this, it just looks like the area beneath the curve itself. Okay, so the more rectangles we have, the closer we're going to get. So if we maybe added a 0 to this and went out to, say, the thousands place, well, now we don't see much of a difference between these numbers now. I'm at 5,000 rectangles, and we have 170.6, 170.7, 170.7 when you round. Okay, so the differences between these get smaller and smaller and smaller the values themselves get closer and closer and closer and closer. And what we're approaching is that actual area beneath the curve. Okay, so that is the overall basic idea of how this works. Okay, what's left to talk about is not much different than what we were dealing with right now. But I do want to put a cut in this and come back in a part 2, just so I have the time to look at another example. I'd like to show you all another example and then talk about some notation that can help us make this look a little nicer, right? So you'll notice that when we wrote this, that it started getting kind of monotonous with all these plus, right? So we're going to introduce some notation to kind of help us there, but also another example. So I'll come back in a part 2 to do that extra example. So I'll see you all in that one. Cheers.